Physics. Today we're talking about simple machines, and I always like to start this lesson by talking to you about what simple machines are so you have some context here. This is a lesson where if we don't take some time to put it in context, you learn a bunch of equations that have no actual meaning, and that's of course not the purpose of physics, right? So simple machines are devices that are not battery operated or electrically operated or gasoline or propane powered. They're machines that are manually operated. And I want to kind of broaden manually operated. Typically we think about manually operated as operated by your hands, but it could be operated by your feet. It could be operated by any part of your body, but you're physically having to do work to operate it. That's the key to a simple machine. So a simple machine, look up here for a moment, could be a pulley system. I have to do work when I pull on this effort rope. And the work that I do, if I measured it, would be equal to the force that I use to pull the rope times the distance that I pull the rope. The purpose of a pulley system is to lift something off the ground. So the work that the pulley system does is it creates the gravitational potential energy of this object once I lift it up. Now, do you notice with this pulley system that I have to move my hands a lot further than I'm actually lifting that weight?
Yes, sir.
So that means I'm doing the work over a large distance, but I'm actually not getting to lift this object I'm trying to lift very high. That distinction in the distances is what gives this machine purpose. Simple machines take work that you do manually and they turn it into work that you couldn't have done otherwise. Now it might seem weird to take an object, to have a machine to take work and just turn it into work. But what a simple machine does is it changes the nature of the work that you do into the work that you need done. In the case of a pulley system, I typically wouldn't set up a pulley system to lift a kilogram. I typically set up a pulley system to lift a car's engine out of its bay, or lift something that's really heavy that I couldn't otherwise just grab and lift. So a pulley system, I'm going to put some examples of different machines here. A pulley system would go on this side of this slide, because what it does is it takes the input force, that's the force that the person actually exerts as they operate the machine, and it turns it into a much larger force. With a pulley system, you can lift something that's heavier than you could lift without it. But if you get force multiplied, and that's what the font difference here is supposed to represent, it's taking a small force and turning it into a big force, which is why we're using the small font, big font. It's always at the cost of distance. You saw that I had to move my hands a lot further than I actually lifted that weight. Since work is the product of force times distance, the work input equals the work output. So machines like this, like simple machines, like a pulley system, you do some sort of physical work to operate the machine, and it does some physical work for you that you couldn't otherwise do without the machine. That's the purpose of a simple machine. So let me give you some other examples of simple machines. And then what this is going to lead to is I'm going to ask you to kind of tell me an object that you think is a simple machine, and I'll tell you whether it is or not so that we know what we're talking about, and I'll also tell you where it belongs. Does it make you stronger, or in the case of some devices, it makes you faster? A bicycle is such a machine. It's actually a collection of simple machines, gears, wheels, cranks, all sorts of stuff. But together, a bicycle actually takes the force that you push on the pedals with and makes it smaller. The bicycle's wheel pushes backwards on the ground with a force that's actually smaller than the force you push on the pedals. But the distance you move your feet is a lot smaller than the distance that the bike actually moves when you pedal, which means that you get to go further and not move your feet as far. So a bicycle doesn't make you stronger, it makes you faster. So there are two kinds of simple machines. There are simple machines that multiply force, they make you stronger. They allow you to do work that you're not strong enough to do, lift something heavy, for instance. And there are machines that actually make you weaker, but they make you faster. You can take the object and make it go quicker than you could without the machine. But if you get one, you can't get the other. If it makes you faster because you can go further, you can't also get more force. If it makes you stronger, it's always at the cost of distance. You're going to do the work slower. So machines either multiply force or they multiply distance, but never both. They can't multiply both because that would mean you get more work than you did, and that would violate the law of conservation of energy. It's one or the other, not both. So now we've reached the time where you shout out something that you think is a simple machine, and I will tell you whether it is, and I'll tell you which side of this slide it belongs on, and if I have it in front of me, I'll actually demonstrate it. Go.
I was going to say belay device, like as I'm climbing.
One at a time. Go right there.
Belay device.
Oh, like the one that grips the rope?
Yeah, it's like a metal piece.
Yeah, that's to add friction. That belay device is actually really just to create enough friction on the rope so that you don't have to pull, you don't have to like hold on to it as hard or change the direction of it. I've helped someone climb, so I think I know what you're talking about.
That's why I'm curious.
Yeah, that thing just adjusts friction. So there are things that add friction or take away friction that really aren't simple machines. They're not transferring work into work. They're just adding friction to the system. The opposite of that would be wheels. Wheels aren't really machines. They just reduce friction. All right, give me something else that you think is a simple machine. Go.
My mallets that I use every day in band.
Your what?
Like my mallets, my drumsticks, but for
Oh,
mallets.
okay, so drumsticks, mallets, things like that. So anything that you swing is a simple machine that's designed to give you more speed. So mallet, axe, hammer, when you're actually hammering a nail, not when you're trying to pry something up. Baseball bat, those, golf club, all of those things work the same way. With a mallet, an axe, a hammer, a baseball bat, or a golf club, what you want is the thing at the end to have lots of kinetic energy. You want a baseball bat to go really fast through the strike zone so that it's got lots of kinetic energy so that when it hits the ball, it can transfer some of that energy to the ball. You want the head of a hammer to go really fast so that when it hits the nail, bam, it can transfer a lot of energy to the nail in one at impact. So by putting the weight out from where your hand is, the manually operated part, the input side of this equation, is what you're doing here with your hand. So look where I'm inputting the force, from here to here. I moved my hand about that distance. But I moved the thing I'm trying to give kinetic energy to from here to here, a much bigger distance. So since I'm moving this weight that I'm trying to give kinetic energy to a lot further, that means it takes more force to do. What that means is it would actually be easier to use a hammer it would take less force to use a hammer or a baseball bat if I just grabbed the heavy part and swung it. The problem is, while it's easier to do that way, it requires less force, I can't make it go as fast, which means it's not very useful because what I want to do is have this thing go fast. I want it to have lots of kinetic energy. So you think about the bigger the job, the harder it is to do that thing, the longer that handle tends to get. So if you think about chopping wood where you're using an axe rather than a hatchet, then suddenly that thing gets real long and it's real hard to swing a heavy axe or a heavy sledgehammer. In fact, we start to take kind of a longer swing to kind of build up the kinetic energy as we do. But still, the distance we move our hands is a lot smaller than the distance that we move the weight that we're trying to give kinetic energy to. So it's making this thing move further in the same amount of time, but it is at the cost of force. That's why you see people when they first swing an axe or a hammer, they reach up and they put their hand closer to the weight, and then as it starts to go faster, they slide their hand down and only for the last part exert the force out there, because the further away your hands are from the load, the bigger this distinction between the input force and the output force, and it's hard to control way out there. Any baseball players out there? What do you do when you've got two strikes? What do you do? So this is a golf club, not a baseball bat, but what do you do when you got two strikes? Yeah. Yeah, you choke up a little bit, right? And why? The point is to make the end of this go fast, right?
You're gaining more control rather than velocity that can be
Right.
Rather than getting a home run, you're gonna get a hit. Of
But at
some
least
kind,
you,
yeah.
but at least you put the bat on the ball. So when you have your hands towards the end, you have less control because the force needed here to exert a force out here is really cut a lot because that object is a long way from you. By choking up, the force required to swing this becomes smaller, but you can't swing it as fast. So you're making it a little bit less of this kind of machine. And of course, if you're bunting, you don't do that at all. You actually grab physically the head of the bat because you don't care how fast it's moving. You want absolute control over where you put it. So then you're not using it like this at all because you're not swinging it. For those of you who are golfers, think about a putter, right? Like you don't need that much power, and so you really want to be pretty close to the head, which is why a putter's short. For if you're driving the ball, golf clubs get progressively longer the further you're trying to hit the ball, right? A long golf club puts the head of the golf club that you're trying to swing really fast out way far from you. They're harder to control, right? Because the force that you input here at your hands is going to become a tiny force on the driver. But then as you swing it, the head is going to move a lot further than you moved your hands, which means it's going to multiply its speed, but at the cost of control over it because the force you're exerting on the head is smaller. That's why your technique has to be so good. So all of these devices that are designed to give something that's out from you speed so that it can impact and do something, like a mallet, if you're playing a drum, you want the end of that mallet to have more speed than your hand could have. And then when it hits, it can deliver all that kinetic energy. Anything like that is going to be this kind of machine that makes you weaker, but you get the end of that thing to go faster. All right, other simple machines.
A wrench.
So a wrench, I got an old pair of pliers, but we could use as a wrench. This is a pretty sweet pair of pliers here. Mr. Lowry found this pair of pliers buried in his yard when he was redoing his fence. I want to find the modern equivalent of this. If you look carefully, you can see it's pliers on one side, but it actually has a hammer on the other side. You know, so often you're kind of prying on something and then you need a hammer, but this is both. You could just turn it around and go whack and then grab the thing. And before it rusted out, you can see it actually had a little place for crowbars here. So I've been trying to find the modern equivalent of this thing because I think it's a pretty useful tool. So when you use a wrench, there's a nut or a bolt you're trying to twist, right? And you grab it, and then you move, I'm going to turn the axis of this so you can see it. You move your hand as you operate it through that arc, yes? But you only twist the nut or the bolt that far, right? So wrenches go over here. Wrenches make you stronger. You can't just grab the nut and turn it anymore. So you grab the wrench. And if it's really hard to turn, you grab a wrench that is longer so that you have to move your hand further as you turn it. Make sense? All right, what else? Yeah.
Stapler.
Huh?
That's stapler.
The stapler. So staplers sometimes have a mechanical advantage built in, and sometimes they don't. So the work you're trying to do here is actually make thermal energy, trying to bend the staple. But you may notice that this one, do you notice that how far the handle moves and how far this moves isn't quite the same? There actually is a little bit of leverage. That's why this is a soft closed stapler. But a typical stapler that doesn't have a separate lever compared to where the staples go, that takes a little bit more force, there is no mechanical advantage. The force you push down on it is exactly the force you're using to bend the staple. Some machines like that, instead of being a force multiplier or a speed multiplier, the purpose of those is to just do some fine work that you couldn't like manually do very easily, right? I mean, you could just push the staple through and bend it. It's just awkward to do because the staple's so fine and your fingers aren't really built for that. So some machines don't really do this. They just have a mechanism that makes the work simpler done by, in this case, a stapler, if you've ever looked at it, it's got two little kind of troughs where the staple, once it hits, kind of follows the curvature of that and it bends the staple for you. But you still have to put in all the force it takes to bend the staple. It doesn't actually give you a mechanical advantage. But this one does. That's why it's a soft close one. Because of that, you have to move your hands further than you actually move the staple, so this stapler belongs over here. Most staplers are neither of these. You move your hand precisely the distance that you bent the staple. Yeah?
Wouldn't the pry part of the hammer go on the left side?
Yeah, so the pry part of a hammer. So any crowbar or a hammer if you're removing a nail would go over here. So think about, here's a nail, look up at me. Here's a nail, I want to get it out of the wood, I hook around it like that, yes? When I do the work, that's the input side, I move my hand from here to here. But I only lift the nail that far. So I move my hand a long way, I lift the nail a little bit, so I'm giving up distance, which means I should get force. This pulls up on the nail with way more force than I am pulling on the hammer with. And the longer this handle, and the closer the nail is to the pivot point, the more it multiplies my force. So yeah, a crowbar or a hammer or a pry bar. I have a big steel rod that I use out in my yard because I live near Lookout Mountain and it's all just a pile of rocks. And if I'm digging in the yard and there's a rock in my way, I put that pry bar underneath and I wrench it out. I couldn't lift the rock, it's too heavy. But because I got that pry bar, I lift the rock this high, but I move the pry bar a lot further distance, so it makes me stronger. Some machines make us stronger or faster, but not both. Yeah, you just mentioned one. Yeah, hopefully not the crime, but the thing you would use to lift up a car.
Oh, yeah.
Right? I have one of those, hang on. So you mentioned the car jack, left side or right side of this slide? Left side, this makes you stronger. So here is a typical jack that is involved, that is kind of given to you with a car. Notice that when I try to lift up, when I turn this crank, do you see how far I have to move my hand? But with every time I turn my hand through that circumference, I actually only lift the car about that far. So a jack is a huge force multiplier. But at the cost of distance, I have to move my hand a really long way to in any meaningful way lift the car up at all. Now, of course, when I have a flat tire, I just, with one hand, I just grab my car and lift it up, and with my other hand, I change the tire. But when you do that, right, you're not strong enough, and so you use one of these, and it multiplies your force. Make sense? All right, yeah. So like a manual one?
Yeah, push it.
So a manual one like that, you are physically just forcing the air in, and so those don't typically have a mechanical advantage. That's like the stapler. It's a mechanism designed to do work that would be hard to do. In that it would be, you don't have a way of holding air in a little space and pushing the air into your tire. So a tire pump, you are literally just having to push the air in. There are not typically any tire pumps that have a mechanical advantage. All right, we understand what simple machines are? You good there? We understand what we're talking about at least? All right. Now that we've identified what kinds of devices we are talking about today, now let's talk about the things we could measure about those devices. One of the things that we can measure is how much work did we do to operate the machine? So how much work did I do here as I manually input work?
4 times distance.
Yes, with force times distance. Another way to measure the work is the output side. How much work actually got done by the machine. When I did my work on one side of the machine, the input side, I get work out of the output side. So with all of these machines, there's an input and an output. When I do work here with the hand I've got closest to you to turn this crank, I get work because I lift the car. The input side is the side you're physically doing. How hard you're pressing on the pedals times how far you move your feet when you're riding a bicycle. How hard you are pulling on the handle times how far you move your hand as you do that. The output side is how hard did the hammer pull on the nail and how far did it pull it? How far did the bicycle wheel push on the ground and how far did you go while that happened? So one of the things we can measure is work input, FD, or work output, FD. Because FD is on both sides, we have to be really careful about knowing in our heads which is which, right? And you'll see me always labeling in and out. Remember that the input side, now I'm going to erase this and go to the next slide. The input side when you think about that, is always what the person operating the machine is doing. So anything else must be the output side. The output side is the work that gets accomplished as a result of using the machine. So in the case of using a jack, it's lifting the car is the output side. In the case of a pulley system, lifting the weight attached to the pulley system, the gravitational potential energy that exists here, that's the output side. In the case of a bicycle, the kinetic energy of you and the bicycle afterwards, that's the output side. From a force distance perspective, this is the work that is input, and that is the work that is output. Now, in physics land, which is our magical place where friction is a force of convenience, we set the work that we do to operate the machine equal to the work the machine does. We ignore the fact that there are, in fact, efficiency losses when you use a machine. In reality, there's always a little bit of the work that you do to operate the machine that's wasted overcoming friction or lifting the machine itself or doing something else that takes away a little bit of energy and doesn't end up as output work. So the efficiency of a machine then is the work that the machine actually accomplishes divided by how much work you had to do to operate the machine. Is that ever going to be larger than 100%? Thumbs up, thumbs down. Is that ever going to be larger than 100%? Thumbs up, thumbs down. Of course, no. That would violate the law of conservation of energy. A machine can multiply force or it can multiply distance, but it can't do both. So you're never going to get more work from the machine than you put into it. Unless you're not talking about a simple machine. You're talking about one that's run on gasoline or battery power. But that's where it got its energy. We can rearrange this equation for output work if we know input work, and of course you could rearrange this one more time to find input work if you knew output. So let's talk about a couple of different kinds of machines. Oh, excuse me, we gotta talk about one more idea. So I've been talking about how machines multiply force or they multiply distance, but not both. So another thing that we can measure is how much does it multiply your force? Or if it multiplies your distance, how much does it divide your force? The term we have for that is called mechanical advantage. So ideally, when you see the word ideal, I hope you read physics land. Ideally, the mechanical advantage is the distance that you move your hands or your feet as you operate the machine, the distance input, over the distance output. How far you lift the load, or how far the bicycle moves while you're pushing the pedals. That ratio is equal to this ratio, the output force over the input force, as long as the efficiency of the machine is 100%. So if a device had a mechanical advantage of 5, it makes you 5 times stronger. If a device had a mechanical advantage of 12, it makes you 12 times stronger.
Or fast.
So if a mechanical advantage, if the machine makes you faster, the mechanical advantage will actually be less than 1. So if the machine makes you 12 times faster, the mechanical advantage is 1/12 instead of 12. Because you've lost force. By making you faster, you always give up force. So the mechanical advantage of a bicycle in any gear is always less than 1. You've probably had the experience of riding a bicycle uphill and at some point going, this is stupid. It would be easier to walk. And so you got off your bike because it was too steep. That's because the bicycle makes it harder to climb the hill. Now, as long as the hill's not too steep, it makes it faster to climb the hill. But at some point, this hill is so steep that you literally would be better off walking and stopping using the machine. And that's because a bicycle makes you faster, not stronger. Once it's too hard to climb the hill because it's too steep, then using a machine that makes you faster doesn't make any sense anymore. You can't do the work with that machine anymore, so you walk. While in physics land, and if the machine's 100% efficient, the ideal mechanical advantage can be found with distance in over distance out. In reality, right, so we're talking about actual. Notice, by the way, we don't normally say actual. If we just say mechanical advantage, we mean the actual one. So that would be in reality, that is literally just the ratio of output force to input force. So if you put in 10 newtons of force and the machine outputs 50 newtons of force, mechanical advantage is 5, it made you 5 times stronger. The distinction between these two ratios is the efficiency. And so if you take the actual mechanical advantage and divide by what the ideal mechanical advantage would be without any friction losses, and multiply by 100, you actually find out the efficiency of the machine. So there's two different ways to get the efficiency of a simple machine. All right. Let's transition now to taking some measurements in real life here so that you can see how to do this kind of problem. So I'm gonna lift an object along a ramp. Typically you don't use a ramp unless you got a really heavy object. So a really common time to use a ramp would be if you're moving. I hate moving. I hope I live in my current house until I die because I do not like moving. Those of you who've moved a lot probably have the same disdain for moving as I do. So if you think about the end of a moving truck, you might set up, if here's your truck, a ramp like that so that you can move things into the truck without having to lift them from here into the truck directly. That's especially important when you've got heavy stuff, right? Now, some trucks have an electrically powered or hydraulically powered lift, and of course those aren't simple machines, so we're not talking about those things. A ramp makes work easier, so it's a force multiplier. And the reason why a ramp makes work easier is the input side of things, where you do the work, is along the length of the ramp. Whereas the output side of things, I sometimes think about the output as like the work that would have got done if you didn't use the machine. What you're really trying to do is just lift the weight. Now, when you lift a weight, the force it takes to lift a weight is its weight. And the height that you lift it is dy. Of course, if we multiply those,
We'll get more.
the work output in this situation would be gravitational potential energy, because it would be mass times ag times dy. The force necessary to lift something is its weight, and the height you lift it to is the distance over which you would have to exert that force if you just lifted it straight up. This is on the output side if you use a ramp, because the ramp actually lifts the weight. You don't directly lift the weight. You exert a force along the length of the ramp, which means you exert a force over a bigger distance than simply lifting it, but that allows you to push with less force than it would have taken to just lift it instead. And the shallower the ramp, the more that is. The more you can use a much gentler force and still be able to roll it up the ramp. The wheels, you usually use a dolly or something like that, right? The wheels just reduce friction so that you're not having to overcome a bunch of friction by sliding the thing up the ramp. So in addition to moving trucks, where else do we use a ramp? Sure, wheelchair ramps, right? Person using a wheelchair typically doesn't have a lot of power or a lot of force, so by using ramps, we reduce the amount of force necessary to climb it, but you gotta do it over a longer distance because the ramp is longer. We also use them at water parks. Have you ever noticed that you always walk up ramps at water parks instead of stairs or ladders, or just jumping up to that height? That's because they know you're probably barefoot and wet feet, you have low friction, so they don't want to put you on something steep and have you slide, so they have you on these really shallow ramps.
It helps you overcome the force of gravity.
It helps you, I mean, you're still able to get up to the top to ride the roller, ride it again, but you're not having to worry about, the limited force of friction since you're, got wet feet. So ramps are also used in low, not very steep ramps are used when you don't have much friction, or you got people who are kind of unstable if there's a lot of friction. Think about learning how to ski at first. You start on a really shallow ramp because you don't really know how to control that. In any case, when we use a ramp like this, we're turning the work we do along the ramp into the work that would have occurred if we had just lifted it. So let's actually make some measurements here. So out in front of me here, I've got a ramp and I've got a force probe so I can measure how hard I'm pulling. And this weighs has a mass of 1.5 kilograms. And now what I'm gonna do is measure the force necessary to pull it along this, that's what I'm looking for, pull it along this ramp. So I'm gonna hook this on to this cart, and you can see if I pull it that way, I can start to move it up the hill. But rather than just pulling it directly, I'm gonna pull it through this force probe so I can measure how hard I'm pulling it. So I'll measure that. Which force am I doing then? Input or output? Input. So let's go to here, and I'll click collect. There we go. There we go. And you notice that force stays reasonably constant as I do that. So I'm going to take the average of that force. So as I was pulling it up at a constant speed, all I was doing was changing the gravitational potential energy. You notice it took a little bit more force at the start because I had to get it going, but it takes a little bit less force at the end because I allow it to coast to a stop. So the force along the way as I'm pulling with a constant speed is the best representation of how hard I'm pulling. And I get a force of 1.757 newtons. So my input force, F in, was 1.75 newtons. Now, I lifted it along the ramp from where it is to that bracket, and that's a distance of 83 centimeters. Distance in or distance out? Distance in. That's the distance over which I did work. So D in equals, I'm going to call that 0.83 meters, right? Centi means 10 to the -2, so I want it in standard units. Now, by using the ramp to pull this up to here, what the kind of energy that ends up existing at the end is gravitational potential energy. This object is up high and it wasn't before. So that has a mass of 1.5 kilograms. That means its weight is mass times AG, so that's 1.5 kilograms times 9.81 meters per second. It weighs, calculated, where's my calculator? There we go. 1.5 times 9.81. It weighs 14.715 newtons. That's the output force. The ramp has to exert a force upwards that's that large in order to lift the object. Now the distance output would be the height to which the object was lifted. That I can measure pretty easily by measuring where it was. It was about 7.5 centimeters up, and where it ends up, it ended up about 16 centimeters high. So we lifted it 8.5 centimeters, is my math right there? I think it is, which is 0.085 meters, about that far. Notice that we didn't lift it nearly as far as we actually pushed it along the ramp. That's what made the work easier. We spread the work out over more distance. So now what can we do with that? If we want to find the efficiency, remember is work out, so the work that actually got accomplished, divided by the work in, the work we had to do to operate the machine. The work input would be the F in times the D in, so that's these two numbers here. When I calculate that, I get 1.75 newtons of force along the ramp times 0.83 meters, 1.45, and there's more to it. And this now would be in joules because it's an amount of energy. The work output would be the F out times the D out. That would be this force. I've got the decimal place in the wrong place. I said 14, didn't I?
Yeah.
14.7 newtons. So the 14.7 newtons goes here, the 0.085 meters that we lifted it goes there, and what we find is we have accomplished 1.25 joules of work. Notice that we had to do more work and we got less out, of course, because we had to overcome efficiency losses. We have to overcome the friction of the axles and the bearings. We always end up doing a little bit more work when we use a simple machine than we get from the machine. But we're able to do the work. So we give up a little bit of efficiency, but we're able to get a job done that we otherwise couldn't do. Obviously, you wouldn't normally set up a ramp to pick that up, right? You would only set up a ramp to roll something heavy uphill. You couldn't otherwise just lift. So the efficiency then would be the 1.25 ... joules over the 1.45 ... joules times 100%, and we end up with, what do you get if you've been following along? I get 0.861 times 100 is 86%. That's close enough to 100 that you see why a lot of times we're just going to estimate that a machine is 100% efficient. So 86% of the work I do to pull this up along the ramp turns into the mechanical energy of the object. By the way, we talked about wheels are friction reducers. If I get rid of the wheels and I instead try to pull this object up when it's sitting on felt, the work I would accomplish, the output work, once I moved this up to here, would be the same. I lifted the same object to the same height. But not using wheels and instead having it slide on the felt increases friction. So watch what happens to the force it takes to do this. Instead of being 1.7 newtons, it's more like 5 newtons. That means that I have to do way more work. So what just happened? When I got rid of the wheels, I put felt down underneath instead.
Increase the friction.
I increased the friction, which changed what about the machine? It changed the efficiency. That didn't actually change the output work because I still lifted the same object the same height. What it changed is the input work. I have to do a lot more work now to overcome the inefficiency of that machine. Which is why you typically wouldn't do it that way, right? If you're using a ramp, you put the thing on a dolly so that you can roll it up the ramp and reduce friction along the way. You're trying to get rid of the inefficiency. All right, questions about what we just did?
No, sir.
Hey, was the mechanical advantage of that ramp as I just used it greater than 1 or less than 1?
Less, because you increased distance rather than.
Careful. I put in 1.75 newtons. I got out 14.7 newtons. Mechanical advantage is greater than 1. This may be stronger.
So your distance in was less than your distance out though?
No, it wasn't. My distance in is 0.83 meters. My distance out is 0.085, right? So ideally, the mechanical advantage here would be 0.83 divided by 0.085. When I do a little back of the napkin calculator here, 0.83 divided by 0.085, that should have made me 9.7 times stronger. That's the ratio of this distance to this distance. But it actually made me 14.7 divided by 1.75. 14.7 divided by 1.75 is 8.4. So it actually made me 8.4 times stronger. Pretty close to the 9.7 times stronger it was supposed to make me. And that distinction is because of the 86% efficiency. But I've got a mechanical advantage bigger than 1, so this may be stronger. But I had to push it a lot further. All right, let's apply this to a pulley system and learn some things physically about that. Before I erase this, questions?
Sir.
Okay. If we look at a pulley system, there are some things about the pulley that allow us to figure out how it functions without having to make a lot of measurements. For a pulley, the number of support and effort ropes actually tells us the mechanical advantage. So, watch this. This has one effort rope and 4 support ropes. Can you see them all? Now, when I lift this weight at the bottom using this effort rope, this is 80 centimeters from the table. So if I move the effort rope 80 centimeters, do you see that I do not lift the weight 80 centimeters? I've lifted the weight 20 centimeters. So what is the ideal mechanical advantage? I moved my hand 80 centimeters, but I only lifted the weight 20 centimeters. 80 to 20 is 4 to 1, right? This should make me 4 times stronger. And here's how it does that. The tension in the cord is the same everywhere in the cord because it's the same cord. But I'm pulling with 1 cord. This is getting pulled with 4 cords, which means each one of these ropes is pulling up with the same force that I am, but there are 4 ropes pulling, which means I get 4 times the lifting force that I pull with. So this multiplies my strength by a factor of 4, but at the cost of the distance by a factor of 4. I can't lift it. I have to move my hands 4 times further than I actually lift the weight. But as a result, I get 4 times the force. So if this were really heavy, I might be able to lift something that's 4 times heavier than I could actually just lift on my own. But I'm going to have to move my hands a long way to do that. Make sense? So that's how this works. Hey, this is 1 kilogram. So what's it weigh?
100 grams?
No, kilograms of mass. Careful, kilograms are mass, right? This is 1 kilogram, so what's it weigh? 9.81 newtons, or 9.796 here in Denver, yes? Can we approximate that as 10?
Yeah.
This weighs about 10 newtons. All right. What should be the force that I measure right here?
Yeah, 2.5.
Yeah, about a quarter of that, right? So I had a scale just here. Where'd it go? Where'd my scale go? I don't think so. Oh, why am I being dumb? Here, can't I just do this? Will you go ahead and collect? Oh no, you don't. Hang on, I got. So if I click collect here and I pull, we can see that the force is, there we go. There's 5 newtons, there's 0, there's 3, so the force is about 3 newtons or so.
Yes.
Why isn't it 2.5? Because this isn't perfectly efficient, right? So ideally, I should only have to pull with a force of 2.5 newtons, but I actually have to pull with 3. Part of the reason when you use a pulley system, you have to lift the pulleys themselves. And so part of the weight you have to lift is these pulleys, not just this. So again, I'm gonna end up doing a little bit more work here than I got accomplished. But if I'm trying to lift an engine out of an engine bay, who cares? I'd rather do a little bit extra work and be able to do the job. All right, there are other machines where, like for pulleys where we can count the ropes and figure out something about how it works. There are other machines where we can just look at the machine and figure out something about how it works. One of those machines is a lever. So when we use a lever, the length of the output arm, we also call it the load arm. And the length of the input arm, the ratio of those tells us the mechanical advantage. Because how far we would have to move our hands as we use a pry bar or a lever, that distance is proportional to this distance in the same proportion as the length of the arms. So when we use a hammer as a lever to pull a nail out, that's why the distance from where you put your hand and the pivot point, that would be the effort arm, and the distance from the pivot point to where the nail is, that would be the load arm. That ratio tells you how much stronger this makes you. Hey, old cars, like pre-power steering, have big steering wheels, yes? The steering wheel is actually a lever. In old cars that don't have power steering, you are physically turning the front wheels when you turn the steering wheel. And if you don't know how hard that is, shut your car off, but have the key on and try to turn your wheel, and you'll figure out how hard that actually is. Modern cars tend to have small steering wheels, and one of the reasons they can be small is they have electrical or hydraulic powered assist to help you turn the wheels. But old cars don't have that, and so the steering wheel is huge so that the effort arm is longer, you move your hand a lot further, but you're able to actually turn the wheels.
And this is increasing force.
That increases force. The bigger the steering wheel, the less force you have to use and the more force you get out. If it's a tiny steering wheel, you really have to just wrestle the crap out of that to actually turn it. Your input force has to get bigger because it's not multiplying your force as much. It's also interesting to think about a wheelbarrow is actually a lever. We don't typically think of it that way, but where's the pivot point for a wheelbarrow? The wheel. So the fulcrum, so whatever the pivot point is, that pivot is also called a fulcrum. So either word is fine. For a wheelbarrow, that pivot is there. You put the load here. So the effort arm, or the load arm, is that long. But you lift here, which means the effort arm is that long. When you use a wheelbarrow, you don't really lift this load very high, but you're able to lift it. And those of you who've used a wheelbarrow know that if you're trying to lift something really heavy, you put it towards the front of the wheelbarrow so it's more over this fulcrum, and then it's easier to pivot. If you have all the weight in the back of the wheelbarrow, it's harder to lift because it's closer to where you're actually doing the work, which means you're lifting it just as high as you're moving your hands. The wheel is just a friction reducer. Once you've got this part lifted off the ground, then you're just rolling it around, and the wheel allows you to move it from place to place without having to overcome much friction. But the reason why the handles are longer than the load is so that you can do the work out further from the pivot, making the force you need to lift it less. Next machine we want to talk about is a bicycle. And this is our last slide. I talked to you about how a bicycle is not a force multiplier, it's a distance multiplier. These make you faster. This helps you to understand why the distance the bike actually rolls would be the distance that the wheel turns, yes? The distance that the wheel turns is much larger than the distance your feet turn in any one particular revolution. That means the input force has to be bigger than the output force. And that's why once the hill is too steep, you just go, this is done. Why am I using this? And you get off and walk. Because you'd literally be standing on the pedals and it's not enough to make the bike go forward anymore. So since you move your feet much further, you move your feet, that's the distance the pedals move, a lot less distance than the distance the bike actually rolls. The mechanical advantage of a bicycle would be less than 1. That's why it makes you faster, not stronger. Another fun device that makes you faster, not stronger is there we go. A salad spinner. If you want to dry off your lettuce, you might want your lettuce to go really fast. Spinning lettuce doesn't take that much force, but spinning it fast, you might not be able to spin it as fast. You want to spin it faster than your hand can go. So that slide right there showed you how you use this simple machine. You input the work right there. Let's do it again. So here's the input work, pushing down through that distance. The output work is the kinetic energy of the lettuce as it's spinning around. You notice that the lettuce is moving way faster than her hand. If you've ever used a salad spinner, you know that it actually takes kind of a meaningful amount of force to operate it. Because this, like a bicycle, makes you faster, not stronger. The lettuce goes way faster than your hand is going, but you have to push pretty hard on that button. There are some salad spinners that use a crank and they use the same idea. So in order to make the lettuce go faster than you could move your hand, you set up this device that increases speed, but at the cost of force. And that's why it's so hard to push the button, even though you're just moving the lettuce. But once you get it going fast, the inertia of the water carries the water out towards the outside of the container, and since the container the lettuce is in has holes, then the water can spin out just like clothes in a spin dryer, and the water is collected on the secondary hull that's the complete plastic. So a salad spinner also makes you faster, not stronger. Okay, the first problem that you're going to do in the practice deals with a mechanical lift There's lots of mechanical lifts. Here's one that's designed to attach to a tailgate. So you can see it's hand operated. You would do the work turning that crank, and then it would lift the object. These are usually used when you're too weak to lift the thing on your own. So the input work here is at a smaller force, but a bigger distance. You're gonna move your hand a lot further as you crank it around than you actually lift the object.
That doesn't make any sense in the context of the first problem, because it's saying the input is 2.5 and the output is 1.0.
That's work, not force. We must make a distinction between the two. If the input and output work don't equal to each other, it's because the machine is inefficient. Here are some other kinds of mechanical lifts. So you just have this in perspective as you're doing that first problem. So here's one where the mechanical work you do is with a lever, and it basically acts like a jack and moves it up a little bit at a time. This one, you can see there's a hand crank, and so that hand crank, this is cable operated inside, and it lifts them up. This one, it's very easy to see that it's hand crank operated, so this has kind of a tower and a cord that goes over the top. You do your work here, but the work ends up getting done by the machine to lift the load. So there's actually ones that'll lift a car that are like this. You have to move your hand a long way because you're lifting something really heavy compared to how far you lift the car. Questions? All right, so we got a little over 15 minutes. I want you to do 24, 25, 26, 27, and 28. The math here is not difficult, but identifying what's happening is typically the stumble. I would recommend you draw a picture and remember, the input side of what's going on is always what the operator of the machine is doing. The output side is the work that would have gotten done if you didn't use the machine. You just got the work done. I'll be walking around helping you out.